name is Mike Dubson. I'm from the University of Colorado at Boulder, and I'm going to talk to you today about how to use these PhET interactive simulations in the classroom. So how many of you have actually gone to the PhET site and actually played around with the sims? So maybe a third to a half of you. Very good. So if it was 100%, I'd feel like I was in the wrong room. So I'll teach some of you some things. So what's PhET? It originally stood for Physics Education Technology Project, but now it's just a brand name like Kleenex because we no longer just do physics. We do math, chemistry, some earth science, some biology. It's a collection of more than 100 interactive sims for science education. They're all based on research on how people learn, and they're all user tested. So they're written in either Java, Flash, or HTML5, and they run in your browser or offline. You can download everything and run it offline if you're going to be in an environment that has limited internet connectivity. Like I said, they're mostly physics sims, but there's also a lot of math and chemistry, some earth science, some biology, and everything's free, 100% free. Our motto is, this is the best science education software money can buy, except you can't buy it because it's free. Right. Because they have the fewest platform issues, and the oldest ones are Java because they're kind of an hassle to start. Java and Flash will not run on tablet devices. So in order to maintain market share, whatever that means when our product is free, we have to switch to HTML5 to catch the tablet market because more and more that's where K-12 education is going. They're using iPads in grade schools. Okay, so where is PhET? It's at phet.colorado.edu. So you have a couple of handouts. You have this one handout in your booklet, and then there's a second handout called Creating Interactive Simulation Activities, which I think Stephanie authored. Stephanie, are you the author of this? Yeah. Reviser, okay, very good. And then finally, I'm going to ask you to pull out. You actually don't need these for this workshop. I just wanted you to know of their existence. But something you will need for this workshop is this thing you got from Ed Prather the other day. So could everyone pull out your card to vote with, because this will be an interactive presentation. So I want to start by just giving you a couple of examples. I want to show you our two most popular PhET sims. They are Circuit Construction Kit and Masses and Springs. So let me just go to Circuit Construction Kit here. So this is just a toolbox with light bulbs, batteries, wires, and switches. I'm just going to build a simple circuit here. Let's see. Let me hook up the light bulb to the battery and the switch. And then I'm going to close the switch and see if the blue electrons flow. So here I'm going to close the switch. Ta-da! Okay, light bulb is on. You can build a circuit of any complexity with this sim. It's completely general. We also have an AC version where you have capacitors and inductors. We try to make the sims as accurate as possible, but sometimes we are inaccurate for pedagogical reasons. For instance, you see the blue electrons. Electrons aren't really that big. But more to the point, they aren't moving nearly that fast. The drift velocity of electrons in a circuit is about 100 times slower than that, and you wouldn't see them move on the screen unless you watched for a while. So we speeded it up for pedagogical reasons. Okay, another real popular sim is called Masses and Springs. It's just a little laboratory here with springs and masses, and I can change the amount of friction. I can change the stiffness of the spring. I can make it very stiff or very floppy. And then I can do things that are hard to do with springs. I can change gravity, go to Jupiter where gravity's strong, go to Earth where gravity's lighter. Let me turn friction back up here. I've got a stopwatch, so I can time things. I've got a ruler here, and I can zoom in if I want to take careful measurements. Let me show all. That's all for that. No, you can't. You have to take the data yourself, and not with this sim you can't graph things. I'll show you another sim where you can graph things. I can show energy conservation here. Let's see, let me slow down time. Whoops, a lot of friction, so a lot of thermal energy there. Turn off friction. Okay, I'm going quarter time here. So here's a energy graph, kinetic potential, gravitational potential, elastic potential, and total. If I turn on friction, I start getting thermal energy in the mix. Questions so far? Yeah.
So do you use softness of the spring instead of spring constant because this is for K through 12 in addition to?
This particular one is for any age. This has been used K-12, college, even graduate school. You know, it's a nice harmonic oscillator is the paradigm for physics, so everyone uses this.
So the point is you don't want to introduce jargon instead?
Oh, right. We try to avoid scary jargon. Soft and hard, everyone knows what that means. We also want short words because we have limited real estate everywhere on the sim.
So your circuit, I didn't see, can you change the sign of the charge carrier?
Absolutely. Oh, no, you can't. Sorry, it's just electrons.
So you can't draw currents.
Sorry?
You cannot draw current.
Cannot draw current. You mean the conventional current versus the electron current? Let's see. So on one of the sims, we actually have an arrow that shows the direction of the conventional current, and it's opposite the direction of the electron flow. Not this particular one. You can, of course, in real life, you don't see the electrons. You just see that. And then you can pretend that the current's going the other way if you want.
I guess you can stick it in an ammeter.
That's right. That's right. We have an ammeter. We have a couple of ammeters, and the ammeter shows the direction. Well, it doesn't show the direction of the current. It just shows the magnitude of the current.
Oh, it's not signed?
It's not signed. No. No. Sorry. Yeah, this is a magic ammeter. We have a real ammeter. Where to go? Sorry. There it is. Yeah, we have a real ammeter where you have to put things in series, but we also have this magic ammeter that you just place things over. Yeah, I like this. Let me show the electrons here. Does the brightness depend on current? You bet. Let me change the voltage on the battery here, and you'll see the light bulb get brighter. Yeah. No, we made everything as accurate as possible. So back to the presentation here. So who is PhET? It's an organization founded by Carl Wyman in 2002. It's part of the Physics Education Research Group at the University of Colorado at Boulder. It's a collection of university faculty, postdocs, K-12 teachers, and software developers. And it's a big group with a budget of about $1.5 million a year right now. And the reason it's running is because of this person right here, Kathy Perkins, CEO, and I think the most successful grant getter in the world. You know, this is all grants and donations that's running PhET because it's all free. We don't have a business model yet. Sorry, we do. And the name of the business model is Kathy Perkins and her grant-getting ability. Incidentally, she was supposed to be here today, but she's too busy getting money, so I came instead. So we have what's called a Creative Commons license. That means you can use this for whatever you want. You can take our free sims and try to sell them, and some people do. Just as long as you don't remove the logo, you can do whatever you like. We give away the source code. We've made them easy to translate for worldwide use. I'll talk about that later. Let's see. In 2012, we had 40 million sims run. Here are some happy customers around the world: Serbia, Brazil, Vietnam, Uganda. And what is PhET's intended audience? Well, originally it was the audience you're interested in, namely college freshmen and mostly physics sims. But now we've broadened out. We have sims for grade school through graduate school. So at the grade school level, we have a sim called Arithmetic Workout and another one called Build an Atom. But at the upper division, we've got quantum mechanical tunneling and normal modes. We have a lot of math sims as well as physics, and lots of chemistry, and like I said, some earth science, some biology. So let me pause and just ask, how might you use these sims in your school? Pick a topic, any topic, and I'll see if there's a sim for you. Optics. You bet we got some optics sims. Funny you should mention that. Right now, I'm building an optics lab sim, which is much more sophisticated than the following one. Geometric optics. This is Unlikely, because I'm writing it in HTML5. That means I have to learn HTML5. Let's see. So we've got just a simple one lens, couple of sources here. Let's see. Let's show the screen here. So I've got up to 2 light sources here. I can change the refractive index or the curvature or the diameter of the lens. It's very simple, but we're building a much more sophisticated one right now that'll do lenses, mirrors, stops, all good stuff. It'll be basically a full ray tracing diagram program. Deflection of beams under load. Boy, this is great. We don't have that, but I'm also working on that one. It's called Bridge Builder. So we're making a Bridge Builder sim where you construct something and then put a load on it to see at what point it fails. Pardon me? Truss Builder, right. But there's nothing to stop you from just building a bridge with just a beam sticking out and see what it does. Other. Sorry?
Biophysics?
Biophysics? Sorry, we got basically nothing.
But maybe diffusion.
We have a sim that shows some diffusion, but no. The real answer is no. And the reason is we don't have a biophysicist on the team. Yeah.
Biophysics, there's PhET.
There's what? Yeah, but that's not us.
What about condensed matter?
Condensed matter, we've got, well, let's see. Let me think about that. I'm a condensed matter physicist, or at least I used to be. So let's see. What have we got on that? We do have a sim, which I don't much like, called about semiconductor physics, but I don't much like it, so I'm not going to talk about it. Yeah. Brownian motion? Oh, gosh, let me think. So we've got a sim called optical tweezers, and it does show Brownian motion of the DNA molecule. So it's not specifically about Brownian motion, but it's in the code. Yeah?
Do you have any astronomy?
Oh, thank you for asking. This is one of my favorites. It's called My Solar System. It's up to 4 bodies, and you can just set the initial positions and velocities. So this is a Earth, Moon, Planet system here. Let me start it up. Let me turn off the traces here so you can see a little more clearly the little planet going around the sun, satellite going around planet, going around sun. We've got lots of presets here, so you can do nice things like double binary star system with a planet. Imagine the weather on that planet.
How about some wave reflections from the big stand?
Oh, some wave reflections?
You know, big stand, mechanical waves.
We've got, man, yeah, of course we got that, yeah. Wave on a string. So we got more than 100, and projectile motion, pendulum, you name it. Come on. We do not have that yet. Oscillate. A pulse. Okay, here we go. Here's pulse.
Do you have a bet on something that you thought was wrong about the last section?
Pulse. Here we go. Okay. Turn off the friction. Okay, turn off damping. Yeah, here we go. Pulse. Bang. Out it goes. Room. Oh, you want to see the loose end? Okay. All right. Pulse. Well, you guys can play on your own time, but here we go. Okay. You guys are great. All right. All right. So, okay, so we've just been talking about what sims are there. Almost anything you name, except something obscure like Fresnel diffraction, we've got a sim on it. So how might you actually use a sim? Just assume we've got a sim on it. How might you use it in your classroom? Any ideas? Yeah?
I teach in optics studio. I can really benefit from just showing a couple of them from time to time.
Mm-hmm. So basically use them as lecture demonstration in lecture. Yeah, I use them a lot for that.
Which is much quicker than an optic demonstration, so I can spend just a minute on this.
That's right. No setup, no tear down, and it works every time. Yeah. You assign them as homework. Excellent. Yeah, great. So the student is forced to take data or at least do some interactivity before they write something.
For a lab as well.
Uh-huh.
The 2D collisions.
Great. Laboratory. Excellent. So we've designed them for versatile use. So you can use them for anything. People use them for pre-lecture assignments, interactive lecture demonstration. I use them a lot for that. Clicker questions. I'll give you some examples of using PhET sims around clicker questions. In-class activity, lab or recitation activity, homework. But of course, there's no silver bullet. The context and the activity that you build around the sim is critical. Yeah?
Do you guys put together any kind of, make any materials available, like an investigation?
Absolutely. In fact, the problem with our materials is we have too much. So if you go, I was going to get to this later, but let's just do it right now. If you go to any sim, let's go back to the website here. Yeah, here's Wave on a String. If you go to any sim, you'll see a teacher's guide, but then you'll see a whole bunch of teaching ideas. So if it's a gold-starred material, it's a classroom activity that we've vetted. We believe it's pedagogically sound. If it doesn't have a gold star, these are just contributed by users. We haven't had the time to look at them, so they may be excellent and they may be terrible. We don't know. The complaint we're getting from users is they don't want 30 activities. They just want one good one. And so we're trying to decide how to improve the delivery of materials. We're actually working on a PhET site specifically for teachers.
Where's the icon for PhET? Not the star, but the PhET icon.
Oh,
Produced by the...
yeah, it's actually produced by us. Tricia Lobine is one of our staff.
If you vet them and they fail, do you delete them?
It's hard to delete stuff. Yeah, because you don't want to offend people. Yeah, we don't give them a star, right? So no star, it means we're not going to tell you our opinion. Okay. Yeah, right. That's right. May not have an opinion. Okay, so let's see. Versatile, you bet. Let me skip that. Okay, some more examples. So friction is one I use in lecture demo just for real quick, seconds here. Let's see. I don't think I ever started it. Oh, yeah, there it is, friction. Thank you. Chemistry book sitting on top of a physics book. That's apt because physics is the foundation of chemistry and everything else. So if I zoom in, I see the yellow atoms of the chemistry book above the green atoms of the physics book, and I can rub them and see what happens when the temperature goes up. Hotter things means the atoms are jiggling more. This is just a one-shot demo. I spend about 2 minutes on it and then move on. If I rub too hard, I start getting wear and tear. Atoms break off. Let me go to Energy Skate Park here and give you an example of using a sim in a concept test. So let's see. Energy Skate Park is, there it is. Okay. So this is a skater, and you can build any, you can build a track of any complication, but let me keep it simple here. Whoops. Let me just get this guy on the track. Whoops, sorry. Get this guy on the track and get him started here. So I can show a bar graph, energy versus time. And let me just stop this guy when he's right at the top of the track. And I've got a potential energy zero line here that I can move around. And I'm going to move the potential energy line up to his starting point. Okay, and then I'm going to ask you guys a question about that situation. Let's see. So I'm going to move the zero potential energy up to the starting point of the skateboarder. Skateboarder still starts from rest. Okay, the total energy of the system is now 0, positive, negative, or depends on the position of the skateboarder. Do me a favor, don't vote yet. Confer with your excellent clicker teammates, your excellent neighbors, for just a second to see if you agree on the reasoning for your answer. Go ahead and talk to your neighbor. Introduce yourself if you haven't already.
Kinetic will go positive, potential will go negative.
Oh yeah, absolutely, absolutely, yeah, right. When is this supposed to go to? 45 minutes, okay. So it goes till,
We're
Quarter after, thank you. Okay. We're good. Okay.
So no plasma physics.
Okay, so on the count of three, on the count of three, the way this works is you're supposed to put it up in front of your head, oh, the chest. Okay, sorry, I missed Ed's talk. Okay, 1, 2, 3, cards up. So it's overwhelmingly A. So let's check that out here. Let's go back to the sim and start this guy off, and then we'll watch the energy graph. And sure enough, kinetic energy is always positive, but now we've arranged the zero of potential, so the potential is always negative. Total energy, positive kinetic plus negative potential is 0. The zero of energy, like the zero of potential energy, is arbitrary. So that's the point of that sim. Let me ask another one here. Oh, so you guys did great on that. Let me ask a much harder one. Yeah, yeah, sure.
Can you build 2 tracks in there, one flat, one with a curve, and run them?
That is an excellent idea. Unfortunately, we only have one skater at a time. So that's a problem. We can make 2 tracks, but we only have one skater. Yeah, that's right. We'd have to record, we'd have to make a measurement and then do it again. But it'd be much better to have them go together. Yeah, well, that'd be yeah, I think I'm going to add to this one. Okay. All right. Here's a much harder question. Here's a circuit, a 3 light bulb circuit. Okay. In this circuit, what happens to the brightness of bulb 1 on the left when bulb 2 up top burns out? And there's a comment here. When a bulb burns out, its resistance becomes infinite. A, bulb 1's going to get brighter or dimmer, or its brightness is going to stay the same. Confer with your neighbors real quick and vote. You guys are great. You're catching on to this peer instruction. Okay. So I'm going to pretend that instead of these colored cards, you guys all have clickers, and you've all clicked in, and you've anonymously submitted your vote, but you've committed to the vote. So let's answer this question experimentally. So let me go back to electric circuit lab here. Let me clear this, and I have previously I've previously created a circuit which I saved. So I'm just going to open my saved circuit, and there's the circuit, bulb 1, 2, and 3, and I've got a switch in series with bulb 2. Let me turn off the electrons here, because those just confuse things. Okay, I'm going to open the switch on bulb 2, burning that one out, and we're going to watch what happens to bulb 1. You ready? Whoa. It got, what did it do? Got dimmer. Yeah, okay. So now how many of you were right? You don't have to answer. But you know, after people have committed to an answer and you show the results on the screen, boy, everyone just leans in. Ooh, did I get it right? Yeah, sure.
So, sort of a philosophical point. You said, let's check this out experimentally.
Yeah.
This is a simulation.
Correct.
Does that bother you? Is there any pedagogical issues there?
Yeah, I often make that comment that I make the comment to the students that you guys are way too trusting. Okay, if it's PhET, I guarantee we've made it as accurate as possible almost all the time, but we do cut corners or change things like the speed of the electrons. Yeah, that is an interesting point, and all I can do is assure the students that we've done nothing intentionally deceptive.
And I trust you. I mean,
yeah,
it's
right.
not a question of accuracy. It's more a question of the student. I mean, in some sense, you're reinforcing the idea of just, well, I know the answer and I'm telling you.
Right.
Now I have a pretty picture to do it.
Right. I used to do this. Right.
But that's not the same as a lab, right?
Well, I used to do this with real light bulbs, but the problem with real light bulbs is the students couldn't really tell where the wires on the table were. Yeah, right, yeah. Yeah, I'm afraid I don't have a good answer to your question. Yeah.
I can comment,
I would not do it instead. Yeah, I mean, I guess that's.
If I can comment what I did in this case, I had a similar experience with this. I did a simple light bulb experiment where I showed that you get steamer, and then I used PhET for a slightly more complicated setup and to show the current that was going through it. Yeah. So that way there was a connection.
I call things numerical experiments.
Yeah.
There's also been studies that showed students doing electronic labs with simulated like breadboards are more effective because students get really confused by things that don't matter like wire color, and with with a nicely designed simulation you can control those kind of variables that don't actually matter and help the students see what it is. So sometimes
Kathy's giving my talk. This is great. Keep going. This is great.
So certainly for an experimentalist, I mean, there are two different goals. So the real world is more complicated. You are intentionally
Right.
leaving out a lot of physics. You're not cheating, but you're leaving out a lot of things. So.
This discussion is just perfect. Thanks very much. I have another concept test here having to do with a sim called, this is called Kerr Fitter here. So I'm doing a linear fit here. I can do a quadratic fit. I can, it's real time. I can change the error bars here. And this is the chi-square statistic over here on the left. Let me do a linear fit with, let me clear all, do this again here. Let me do a linear fit with 3 data points. Okay. Now let me ask a question about this situation. Sorry, I keep switching around. Okay. So I'm going to increase the error bar on that data point right there. If we increase the error bar on that data point, what happens to the slope of the best fit line? It becomes more negative, that is, the line starts tilting clockwise, or it becomes less negative, more shallow, it starts tilting counterclockwise, or it doesn't change. Again, confer with neighbors before you vote. Yeah, this is a, that's right. This is a weighted best fit line, right? Error bars. Are we ready to go? 1, 2, 3. Cards up. Okay, we're getting a mix here. Cards down. Let's find out. Incidentally, the great thing about clickers is it's anonymous, except when every single person answers wrong. That happened to me once. For this question, a group of middle school biology teachers, every single one of them got it wrong. Okay, so let's find out here. Okay, here we are. I'm going to increase the error bar on this data point here, so I'm going to make it bigger. There we go. Of course, if I make the error bar big, this becomes a bad data point, and a weighted fit will start to ignore it because bad data is just doesn't affect the fit much. But all the biology teachers, middle school biology teachers, thought, well, if the error bar is wider, it's more likely to capture the line. It's a bigger data point, so it's somehow more important. No, it's less important. Okay. So, so why is PhET successful? Well, we have a diverse design team, lots of expertise in human-computer interface. But this is the main reason it's better. We do user interviews. We test whether or not the simulation is pedagogically useful. We do classroom testing. So we don't publish anything until we're convinced it's easy to use. Our design philosophy is we want to have an inviting, not intimidating, intuitive interface, usable without instructions. That's key, usable without instructions. You can tell which are the old Sims because the old Sims have a help button. But we realized after hundreds of hours of interviews, no one touches the help button except old people. People like me. Ooh, there's a help button, but a kid would never touch a help button. So we just started leaving the help button off. The point is, if you can't figure out how it works after just a few minutes of playing, then the interface is too hard, too complicated, and we redesign it. Highly interactive, instant animated feedback is the key thing here. Accurate dynamic visual representations show the invisible. So there are lots of situations where the physics just doesn't lend itself to a visual representation. And so we don't have sims on those topics unless we can figure out how to make them visual. Allow actions that would be difficult or impossible in the real world, and try and make a game-like environment. Inviting is the key. And an interface design that implicitly scaffolds inquiry. By that I mean we have just enough controls that the student is drawn to explore and not get intimidated. Most people are surprised when I tell them it's about $50,000 a sim. Your thoughts? Let's compare these tools. On the left we have the virtual world, and on the right we have the real world. I heard some excellent comments about the comparison of these two just a few minutes ago. Could someone restate those things that I heard said a few minutes ago? These are different.
In the real world, it's very difficult for students to track the wires and understand what is actually connected to what.
Right. The topological complexity of the real world is I remember that was an issue I had. Just converting the simple circuit diagram on the left to a nest of cables on the right.
It is obviously a complementary tool. It cannot replace the right one because you don't learn how to solder these wires, and you need this if you want to do this. But on the other hand, you cannot let them solder for an hour, right?
Yeah, that's right. Then they're not learning the physics, yeah. Soldering is an important skill.
And for a couple of simple examples, you probably can also show them and say, okay, get this.
Mm-hmm.
For example, aligns to mirror system.
Okay, you guys have caught on. I don't have to teach you anything. PhET has penetrated. Oh, yeah.
Question. Do you get a complaint from instructors that those are used as cheat tools for students that they give them the classical problems like a bunch of power supplies, crazy, parallel series. I don't have to do anything. I just go to the PhET website, I build one, and they could ask me if I remove bulb A, what's going to happen.
Yeah. So, yeah. Is that? Do I consider that cheating? Certainly not. If a student, usually there's an assignment. Show, and if a student is using PhET to check their work, great. If the student's using PhET to bypass thinking, then of course that's a problem. But we just haven't had those kinds of complaints. Students get all kinds of tools available on the web. Yeah.
Yeah. You said you didn't want to talk about semiconductors. Is there a problem with that simulation?
Yeah, I just don't think it's very. I don't think it's user friendly.
It would be interesting for you to walk us through one that you think isn't good.
Oh yeah, boy. Sort of like showing the ugly child. Yeah, I'll be happy to talk to you afterward about that. So, comment. This point has already been made in the discussion, but there's this comic strip called Strange Quark about nerds. The researchers at PhET have developed a large set of physics simulations. They found that working with a computer simulation allows students to focus on concepts. They are then better prepared to deal with real experiments with all of their glitches and complications. We couldn't have said it better. We don't know these people. They're not working for us, but they keyed in exactly to what PhET's about. Oh, it goes on to say what they really need is a sim showing you how to date, but that's a... Okay, so can PhET sims replace real equipment? It's already been answered. They can, but we don't think they should. The sims are meant to complement, not replace lab equipment, because the sims lack real-world dirt effects, which are important to learn if you're going to become an experimentalist. But the sims allow students to focus on the physics concepts and not worry about the dirt effects. Sorry, Kathy here was alluding to a study comparing use of virtual lab to a real lab. So this was a few years ago in our algebra-based physics course. It was a 500-student class. We cut the class up into two halves, 250 each. Each group of students had 4 circuit labs to do. One of the groups did the circuit labs with wires, light bulbs, switches. They actually assembled things with their hands. The other group did everything with circuit construction kit, just the virtual lab. And then at the end of the 4th week, all the students had to do a quiz, a lab practicum, where they had to build a circuit that they had never seen before. Build the circuit they had never seen before and answer a question about its behavior. The students who had been doing the virtual lab for 4 weeks had never before touched a wire, and they were touching wires for the very first time when they were doing this quiz. And the students who worked on the virtual lab did just as well. In fact, they did slightly better than the students who had been working with wires. And you could see the difference in the classrooms. In the classrooms with the real wires, the students were very scared that their apparatus would break. So once they got it working, they would say, oh, don't touch it. Bring the TA over to see that it's working before anyone touch it. But the students who were doing the virtual labs were experimenting with lots of different circuits because they knew nothing could break. We saw lots of risk-free rapid inquiry in the simulation room that we didn't see in the real classroom, sorry, in the classroom with real circuits. So I'll bet you know the answer to this one. Do students learn if I just tell them to play with a sim? Of course not. Guided inquiry is essential. That's why we provide this large database, this too large a database of classroom tested activities available on the PhET site. We do ask teachers that they only submit activities to us if they've actually used them in the classroom. We don't want someone to say, oh, wouldn't this be nice? No. But we're trusting them when they say they've used them in the classroom. So what makes a good sim activity? Here's the key idea, the key point. Minimum instruction. Detailed procedures actually inhibit student exploration. Just give them clear learning goals. Give students the goal, not the procedure. Now, we're all teachers and we all think that it's our job to explain things clearly. But I'm telling you, there are some situations where that's not the right thing to do. That's such a strange idea for some teachers that I'm just going to say it again here. For an in-class activity or a lab, the worst thing to do is to give detailed instructions on how to use the sim. We've designed the sim so the students can figure it out on their own. If you give detailed instructions, the students focus on the instructions and ask, they're reluctant to experiment. They ask lots of questions about the sim use, namely your instructions, and not about the learning goals. It's much better to just provide an activity and don't offer any pointers on the sim itself. The students will explore uninhibitedly if you don't give them detailed instructions, and they'll find and learn all the controls on their own and become the owners. Here's an example of a good activity. Masses in spring. Just give them 5 to 10 minutes of play. No instructions. Just let them fool around. And then a set of challenges. Just say, using data from the sim, make a graph that shows whether or not the springs obey Hooke's law. You don't have to remind them what Hooke's law is. They all have PCs. They can look it up on Wikipedia. Challenge 2. What's the mass of the red weight? We've got a couple unknown weights on the sim. Don't tell them how to do it. They'll figure it out. Challenge 3. Determine the spring constant in 2 different ways, from your graph in one and with the stopwatch. Now, that's a good activity. Here's a bad activity, which was actually submitted by a teacher. Watch me while I show you the controls. That was step 1. And then step 2 was this detailed cookbook. Measure the equilibrium extension of the spring 1 for each of 3 different known masses and make a graph, et cetera, et cetera. You know, the students can follow all these directions carefully and do it all right, and then at the end when you ask them what did they do, they'll just say, well, I followed the instructions. What do you mean, what did I do? No, what was the whole point of the activity? That was not part of the learning goal for this kind of activity. Okay.
How do you know?
Yes. Yes.
This is an interesting result. So how do you know that?
How do I know that inquiry is more effective than cookbook?
Exactly.
So.
I believe you, but how do you know?
Yeah. So there have been whole books written about how people learn. Stephanie, do you have a good reference? I'm breaking the wall here.
There's a book called How People Learn.
Yeah, that's how people learn, right? So
it's a deduction from some earlier result. That, you know, this fits into the recipe pattern, so it
right.
fits into the inquiry pattern.
And, okay. Yeah, but you yourself have no doubt years of clinical experience where you've seen people follow cookbook instructions. You know, I certainly did that when I was an undergrad, and I remember learning almost nothing.
I would like to point out, though, if like the Institute for Inquiry at the Exploratorium in San Francisco has a professional development activity called 3 Kinds of Hands-On Activity, where it shows you that hands-on is a spectrum, and just like Ed Prather was saying, these are choices and tools that you have. So if this one, maybe a secondary thing would be to give them a new simulation. I don't know how your simulations run in parallel, but maybe then give them a new simulation that then they will leverage maybe these detailed instructions to get ideas for this next thing. Like, so this can be used. But maybe maybe it satisfies an immediate goal, or maybe it's part of another goal. But it's just like, you don't have to disregard detailed instructions, but they have ramifications. It's a choice. It does something,
and a different choice that does something else.
But I like your attitude. Educational research is supposed to be a science where we have data to back up our claims.
Yeah, I was curious whether you had really tested this one versus the previous paper.
Yeah, not me personally. So we're almost done because I've only got 2 minutes left. What would you like to see in PhET? There's a door prize here. If you want to see our sims under development, go to this website, www.colorado, sorry, that's a typo, colorado.edu/physics/phet/dev for development. You can see sims that haven't yet been published. You can also see sims that'll never get published because we don't like them. So what would you like to see in PhET? Because, you know, some of our best ideas for sims are now coming from users.
A transistor.
A transistor. You know,
Bipolar transistor.
Sorry?
Bipolar transistor, not a FET.
Yeah.
A FET model of a FET would be funny. FET. No, BJT.
Yeah, I'll have to think about that. Yeah. Oh, I'm done in 2. Okay. Yeah, I'll have to think about that. We have thought about that, and you know, making it a usable sim is a different thing than making a sim. Yeah.
I like the Brownian motion idea.
Yeah, I do too.
I don't know what is available already, but something like a Lego for molecules where you put atoms together and build molecules would be great.
We have something not quite, you can't just put anything together, but we have things where you can't put some things together, yeah.
I'd like to see something that does like something numerical, like comparing different methods of integration or differentiation.
Wow. Well, yeah, great. Incidentally, we do have something called Calculus Grapher that has all that stuff under the hood, but you never see it. Yeah.
You have nuclear reactions?
We do have nuclear reactions. We have a reactor sim, which I think is pretty good. Shows a reactor going critical. Shows chain reaction, exponential growth. Check it out. It's okay. It's Java.
Do you have a water tank?
We do have a water
wave
tank. A wave tank. You bet. You bet. We've got lots of wave interference sims. Water waves as well as quantum waves. You bet. Yeah.
Do you have cosmology? Those demos are hard to do.
Yeah, sorry, don't have cosmology. We're open to ideas. I'm not sure what you mean by a...
Well, yeah, I mean, there are a lot of things you could do. You know,
yeah, but is there something that's visual?
Expansion of the universe with the graph and showing what happens in different geometries of the universe.
Yeah, right.
Here's a ridiculous one. This is band structure.
Band structure, yeah, we actually have one of those, and we have a... Band structure is part of the semiconductor sim. So take a look at it. I'm not too wild about it. It's just, it came out a little too complicated. And when we tested it with students, even students who had just taken solid state, you know, they didn't learn much of anything. They couldn't make sense of it. Yeah.
If you're going to do the Brownian motion one, why don't you go whole hog and do the full fluctuation dissipation theorem?
Okay. Well, okay, so I'd like to know what the learning goals are, because that's where we always start with. Happy to talk to you about that later. Yeah?
I already forgot what I was.
Oh, okay, fine. So, the future, more sims, of course. Compatibility with iPad, that's, I'm afraid, sucking up all our time right now. We're having to retool to HTML5. For me, the iPad revolution has been a disaster. Because tablet devices won't run Java or Flash, and so all of our sims are losing market share, and we're having to translate them into HTML5. Okay, so I was asked to make this the last graph session feedback. Please take a minute to complete the survey in your packet regarding this session. Your feedback will help us improve future workshops. Thank you. Be sure to indicate the session and/or presenter name and session format. My name is Mike Dubson. Thanks for your attention.